Today we bring you the fourth video in the mass ranges of stars low, intermediate, and high video series. If you have not watched the first three videos in the mass ranges of stars low, intermediate, and high video series, we invite you to watch those videos before watching this video. Those videos are in the playlist 8 Stellar Properties Mass, Luminosity, Temperature, and Chemical Composition. We invite you to stay until the last minute of this video. The timescales associated with stellar evolution vary dramatically across different mass ranges, reflecting the fundamental relationship between stellar mass, energy generation rates, and fuel consumption. Understanding these evolutionary timescales provides crucial insights into the history and future of stellar populations in galaxies throughout the universe. Main sequence evolution represents the longest phase of stellar life, during which stars burn hydrogen in their cores while maintaining relatively stable properties. The main sequence lifetime follows an approximate inverse relationship with stellar mass raised to the 2.5 power, though the exact exponent varies somewhat across different mass ranges. This relationship means that a star twice as massive as the Sun will have a main sequence lifetime roughly 6 times shorter, while a star 10 times more massive will exhaust its hydrogen fuel in less than 1% of the solar lifetime. The shortest main sequence lifetimes belong to the most massive O-type stars, which may burn hydrogen for only 1 to 3 million years before evolving to become supergiants. These brief lifetimes ensure that massive stars remain closely associated with their birth environments, and they do not have time to migrate far from their formation sites before dying. In contrast, low-mass M-dwarf stars may spend hundreds of billions or even trillions of years in the main sequence, far longer than the current age of the universe. Post-main sequence evolution proceeds much more rapidly than hydrogen burning, typically lasting only a few % of the total stellar lifetime. Low-mass stars may spend several billion years as red giants before ejecting their envelopes and becoming white dwarfs. Intermediate mass stars experience shorter giant phases, lasting hundreds of millions of billions of years depending on their masses. High-mass stars evolve most rapidly after leaving the main sequence, spending only thousands to millions of years as supergiants before exploding as supernovae. The advanced nuclear burning stages in massive stars occur over increasingly brief timescales, reflecting the lower energy yields of heavy element fusion and the increasing energy requirements needed to support the stellar structure. While hydrogen burning may continue for millions of years in a massive star, helium burning typically lasts only hundreds of thousands of years. Carbon burning proceeds for perhaps thousands of years, while the final stages of neon, oxygen, and silicon burning may each last only months to years before culminating in core collapse. These rapid evolutionary timescales for massive stars have important implications for stellar population studies and galactic chemical evolution. The brief lifetimes of high-mass stars ensure that they contribute their heavy element products to the interstellar medium while other massive stars are still forming, enabling progressive enrichment of star-forming regions. This process explains why stellar metallicity increases over cosmic time, and why different stellar populations exhibit distinct chemical signatures. The different mass ranges of stars play crucial roles in shaping the evolution of galaxies throughout cosmic history. The relative numbers of stars in each mass category, combined with their distinct evolutionary pathways and lifetimes, determine how galaxies process their gas supplies, generate energy, and enrich their interstellar media with heavy elements. Low-mass stars, despite their individual faintness, contain the majority of stellar mass in most galaxies due to their overwhelming numerical dominance. These long-lived stars serve as repositories for processed material, locking up hydrogen and helium for timescales comparable to the age of the universe. Their extremely slow evolution means that they contribute minimally to galactic chemical evolution on short timescales, but they will eventually become important sources of enriched material when they finally evolve to become white dwarfs billions of years in the future. The longevity of low-mass stars also makes them crucial for understanding galactic archaeology and the early history of star formation. The oldest stars in our galaxy are invariably low-mass objects that have survived since the first few billion years after the Big Bang. These ancient stars preserve chemical signatures from the early universe in their atmospheres, providing unique insights into conditions and processes that govern primordial star formation and nucleosynthesis. Intermediate mass stars contribute significantly to galactic chemical evolution through their production of carbon, nitrogen, oxygen, and other elements synthesized during helium burning in subsequent evolutionary phases. Their intermediate lifetimes, ranging from hundreds of millions to several billion years, ensure that they contribute their nucleosynthetic products at a steady rate throughout galactic history. The planetary nebulae formed by these stars also play important roles in heating and ionizing the interstellar medium, while dispersing enriched material throughout galactic environments. High-mass stars exert influence on galactic evolution far out of proportion to their numbers. Their enormous luminosities dominate the integrated light from young stellar populations, making them the primary determinants of galactic colors and observable properties. The intense ultraviolet radiation from massive stars ionizes hydrogen in surrounding molecular clouds, creating the bright emission nebulae that trace star formation activity throughout galaxies. Their powerful stellar winds also create hot, low-density cavities in the interstellar medium that can trigger or suppress subsequent star formation in nearby regions. The explosive deaths of high-mass stars through core collapse supernovae represent some of the most energetic events in galactic environments. These explosions inject enormous amounts of kinetic energy into the interstellar medium, creating expanding shock waves that can trigger new star formation while simultaneously dispersing and heating the surrounding gas. The heavy elements synthesized in massive star cores and supernova explosions provide the raw materials necessary for forming terrestrial planets and supporting complex chemistry in subsequent stellar generations. Supernova explosions also play crucial roles in driving galactic winds that can remove gas from galaxy halos, particularly in lower mass systems where the gravitational potential wells are shallower. This feedback mechanism helps regulate star formation rates and explains why small galaxies tend to be less efficient at converting their gas supplies into stars compared to more massive systems. The compact remnant produced by stellar evolution, including white dwarfs, neutron stars, and black holes, continue to influence galactic environments long after their progenitor stars have died. White dwarfs and binary systems can accrete material and explode as Type Ia supernovae, providing additional energy injection and chemical enrichment. Neutron stars can appear as pulsars, whose electromagnetic emission provides unique probes of galactic structure and dynamics. Stellar mass black holes may accrete material and produce high-energy radiation that can affect surrounding gas and dust. You have just watched the last video in the mass ranges of stars low, intermediate, and high video series. You can see more valuable videos by clicking on the card shown here. If you want to see our next video as soon as it comes out, subscribe to our YouTube channel and click the bell icon. Thank you very much for watching the video so far.